A little bit of infrared image analysis in aerodynamics. This episode requires a lot of explanations, so let me describe what you see by voice rather than by text. The last episode showed how thermography can be used in aerodynamics. One aspect was to detect the laminar turbulent transition location. Click the link in the description to watch the previous video. The record below shows the profile performing a continuous sweep. However, since the surface is thermodynamically always a little bit inert, it can happen that one does not observe the thermal footprint of the actual flow. Instead, one probably observes the temperature distribution of a previous flow state. The reason is the heat capacity of the material the model is made of. And because of this, one prefers to first set a single angle of attack, wait a short time for flow stabilization, and then record the infrared image. Waiting for flow stabilization ensures that the infrared image fits to the actual flow state. If the infrared image is taken, the next angle of attack is set and the procedure repeats. Normally, other measurements are done in parallel to the infrared measurements, and if one combines these with, say, lift and drag or a pressure distribution, one can get valuable data about a profile, wing, or a complete aircraft. But since this channel is about infrared or thermal imaging, let's stick to the infrared images only and have a closer look onto them. As mentioned before, from the infrared images, one tries to extract the transition location. There's one important note to make. The laminar turbulent transition is a process which cannot be pinpointed to a single location. It rather starts at some point and develops over a region. In other words, the flow is maybe first fully laminar, but experience small disturbances further downstream. These disturbances will grow over distance and time and eventually lead to a fully turbulent flow. Also, there are different transition types and each one has its own characteristics. Therefore, it is a question of definition where one puts the transition location in the infrared image. One definition could be: place the transition location into the image where the transition process is finished. That means, after the defined transition location, the flow is fully turbulent. There might be other definitions, but let's stick to this one because it's reliable and simple. Before we continue, we need a short introduction to profile or wing geometry. The sketch to the right shows a wing profile. In fact, it's the shape of the famous Epler 374 profile. In general, a profile defines the geometric shape of a local wing section like thickness, nose radius, chord line, chamber line, and many others. For us, the chord line is, for now, the parameter of interest. A profile is often defined in XZ coordinates when working with dimensions. However, aerodynamicists love to compare different profile shapes to each other, and to do that, they use dimensionless coordinates, namely x over z and z over z. The letter c is used for the chord length, which is the straight line distance between leading and trailing edge. If we travel along the chord, we move in x direction, with 0 at the nose and maximum value at the trailing edge. Hence, x over z is in the region of 0 to 1 or 0 to 100%. If we extrude the profile perpendicularly to its own plane, we get a 3D geometry. In fact, we get something which is called a 2D wing because the wing has the same profile at its complete span width. As an aircraft has a span width which is measured from wingtip of one wing to the wingtip of the other wing, the length of a single wing can be called half span or half span width. Let's donate the letter S to the half span width. If we travel along S from inboard to outboard, we move in y direction. Similarly to x over c, one can use y over s to get rid of nasty dimensions. Since we now have our coordinates defined, we can come back to our infrared image analysis. What you see to the right is a series of rotated infrared images. In aerodynamics, the flow is preferred to go from left to right, so I adapted this for our analysis. Each image has been recorded at a specific angle of attack as described earlier. For the analysis, the image contains a blue arrow, which indicates the flow direction, a red line, which indicates the transition location, and a green dotted line, which represents an estimation of the mean transition location. The value of interest is the transition location in x over c coordinates. Remember, it is not possible to see where the transition process begins. Therefore, these lines represent an estimation where the transition ends and the flow became already fully turbulent. If one plots the mean transition location from each image over its angle of attack into a diagram, one gets an overview over the location from which turbulent flow can be expected. This analysis is the most simplest procedure, and it is still useful in times of large computer power and excellent image post-processing tools. This is because infrared images like these can become very hard to analyze by software, mainly because of noise and/or low contrast. However, a big advantage of using dedicated software is a span-wise transition location and not only a single mean value. For using software, one therefore would like to have an image with good contrast and low noise. To increase image quality, one can use internal or external heating. Internal heating describes devices which are built into the wing or model to heat its surface. This can mean the use of an electrical powered heating mat or the use of hot air which is blown from inside onto the structure. External heating makes use of external heat sources. In flight tests, this would be the sun. In wind tunnel tests, this is a strong heat radiation source. Both types of heating have their pros and cons, but describing these would fill another episode. For now, thanks for watching, take care, stay tuned for upcoming videos, and remember, everything is infrared.